Welcome everyone. Uh, Good evening. Welcome to this session of Astro Adda, wherein we have talks given by the members of the Astronomical Society of India. And so this series is being organized by in collaboration between Nehru Planetarium, Nehru Memorial Museum and Library, and the Public Outreach and Education Committee, Astronomical Society of India. And today we are going to uh, go in the radio direction and get to know pulsars a little up close and personal. And we are very fortunate for taking us through that journey with the radio pulsars. We have Professor Avinash Deshpande with us. Welcome, Professor Deshpande. And we have Professor Avinash Deshpande, who has very long experience working with in this field of radio pulsars. He's also contributed to studies of interstellar space through radio studies, and for a long time experience at the Raman Research Institute with cutting edge and innovative instrumentation, and now currently at the Inter-University Center for Astronomy and Astrophysics. We also are joined by Jayant Ganguly. Jayant Ganguly and myself, we are members of the Public Outreach and Education Committee, Astronomical Society of India. And Jayant is going to take over organizing the Astro Adda from next session onwards. So I will hand over to you, Desh, and I just let me just check that I have your. If you will add your presentation in full screen mode, I will bring it into the session. Yes, and it is yes. So the presentation is very visible. There is a kind of a blue band on top right, and maybe clicking hide on it would also allow that part of the slide to be visible. And so I had there is a hide on it. It's okay, even otherwise there is no problem. And so here we are going through the life stories of radio pulsars. I hand over to you.
Thank you, Ratnashri.
Yes, yes, yes,
Yeah, you can hear me, right?
yes, yes, yes.
Okay. Good evening, everyone. Thanks, Ratnashri, for kind introduction and the opportunity to talk in this forum and talk about radio pulsars, which are very fascinating objects. And I will begin by, let's see if the slides are changing. Yeah. Okay. So we're going to talk about pulsars. This particular name was coined by a newspaper reporter when this object's discovery was going to be reported. This particular object involves lots of things that we encounter in various gadgets. It involves primarily rotation. It has a dynamo action. It has large energy storage. It can convert energy from one form to the other, and it has very high space motion. They move very fast in space. There is acceleration in the region we're going to look at more closely. There is breaking of the rotation. There is sparking close to the surface of the star. There is, of course, revolution and emission and radiation coming from these objects, and they are also great timekeepers. Now, we have been spying on these objects for last more than 50 years, and the primary axis along which we can spy these is only the time axis. And that's the only essential information we have from these objects. Of course, as most of you will already know, this story began in 1967 when Jocelyn Bell Burnell, Jocelyn Bell then, was a graduate student at Cambridge Radio Telescope, and her aim was to study twinkling of radio sources. Twinkling not caused by the atmosphere as in optical, but caused by similar phenomena qualitatively because of the electron density irregularities in the interplanetary medium. And she had this transit instrument looking up, and one day she saw these blips of radio signal repeating at regular intervals, the intensity going down this way. And so you will see this periodic appearance of narrow blips, which are separated by an interval which appear to remain constant. So of course she doggedly followed this, separated this from all other possibilities of these signals being produced by local potential sources interfering in this observations, and established that these are indeed astronomical signals. But in doing so, one of the things that one of the lessons that cannot be left unmentioned is for the first time, because one wanted to study intensity variations on timescales of subseconds, that traditional radiometers, or the instruments which integrate for a long time to get a better sensitive measurement, their time constants were turned down to allow for faster variations. And this was amounting to actually opening up completely unexplored parameter space. And it was richly rewarded, as you know, through the appearance of these signals, which were there all along, but you're not allowing them to show up because of smoothing these variations by integrating over a long time. So of course, the initial excitement was tied up with, whether these are signals that we should take seriously as coming from somewhere else other than man-made. Could they be from a spacecraft? Could they be some messages sent by extraterrestrial civilizations and so on? So of course, you can imagine the excitement associated with it. But this was the first evidence for strictly periodic pulses, as seen, as you saw in the chart recorder. And it was that time, as I said, was speculated that it could be a little green man from Mars or something like that, sending messages to us. But as more and more pulsars were discovered, it became amply clear that we are looking at a new class of astronomical objects. And as we know now, that these are highly magnetized, fast rotating neutron stars. Of course, after 6 months of secrecy, the paper announcing this discovery was published in 1968 in Nature. And her supervisor, Uvish, subsequently received the Nobel Prize for this discovery. What is still fascinating to me about not only the discovery, but what followed in terms of arguments that were put together, stringed together to come to a profound conclusion. Each one of them seemingly simple argument. Of course, these are using laws of physics that we invoke, but now each one of them may not imply something profound, but when put together, they really zero down on the possibility of what these objects are. So the first one was about the time followed by these objects. She saw this signal once. She followed it up to see if it's keeping up with the sidereal time, the time kept by distant sources in the sky, or is it following the solar time? And of course, they differ by a significant amount. If you time them properly, it's about 4 minutes a day difference. And if you follow them for sufficient time, you can distinguish clearly whether it's really following sidereal or solar time. So she established that it's following indeed sidereal time, and then that meant that the distances are typically stellar distances, in the sense that it's well outside the solar system. Then, by looking at the pulse width, which was of the order of a few milliseconds or maybe 10 milliseconds, one uses this argument often in astronomy and can, in principle, be used at other uh, occasions as well for a natural situation, where it's called the light travel time argument, where if you see a width of finite width of a particular signal, you can say that the source must be correspondingly small. That means c times the pulse width should be the limit on the source size. Had it been bigger, we would have seen a wider pulse. Now, I will not talk about this pulsating star possibility, but in any case, people thought of other possibilities of being other objects being the candidates, and that time Cepheid variables were very well known as they are even today. And except that the range of periods one saw and the dependence it has on the density uh, suggested that there must be a large range of densities, and that's not possible for a single class of objects normally. And so that was ruled out. Then the other remarkable piece of information that was put together was to see that this object, which has whatever period, the period is changing very slowly. It was noticed that it was changing, but if it's changing very slowly, you can see that this is the energy that it's spending, and the even if you take all that you're observing as an indicator of that lost energy and estimate how much energy it should have by seeing what fractional energy is losing, you will get enormous amount of energy associated with it. And so it implied a massive object. The small pulse width implied a compact object. And so you had a massive compact object. Only two possibilities fitted the bill. One was a white dwarf and a neutron star. Certainly, it was clear that we are looking at things which are of astrophysical origin and nothing to do with the extraterrestrial civilization. So, of course, the possibility of neutron stars being the end result of the death of a massive star was already talked about way before pulsar discovery by Zuki and Bade in their classic paper of 1933, where they said as an end product of supernova explosion, you would get a neutron star. And of course, as you know, it was discovered accidentally 30 years later by Bell and Hewish as a radio pulsar. In the rest of the talk, I will be focusing on rotation powered pulsars and not their other cousins such as magnetars and X-ray binaries. So, of course, in addition to this conjecture that Murray and Zwicky had, it was the white dwarfs lost out completely once the Crab pulsar was discovered, which was rotating about 33 times a second, or 30 times a second, and you had you cannot have a new white dwarf rotating that fast and still keeping itself intact and saving itself from centrifugal disruption. So now the association of it also with the supernova explosion of 1054 AD, formed the connection that one was trying to make. So as we know, neutron stars are dead stars, and they, of course, are remains of when massive stars in the range of about 7 to 20 solar masses explode at the end of their life. Before they really have the explosion, they would have lost large amount of mass and may have still what remains is a small fraction of the original mass. And their masses, the neutron star compact remnant that is left behind has mass between 1.4 solar masses and about 3 solar masses. These numbers might have changed now these are very loose boundaries. And as you know, 1.4 solar mass is the Chandrasekhar limiting mass for the white dwarf. I will not go into details of what is interior of neutron stars. You must have heard about it in other talks earlier, except to say that it's largely neutrons, not only neutrons, and it has got a solid crust, thin crust, and inside it has got superfluid, superconducting interior. The innermost core, where the densities might be extremely high, might have other form of matter like quarks. But in terms of density, it is, as it is said popularly, that 1 teaspoon of this matter will have the mass equal to that of the entire humanity. So that will give you an idea of how dense this subject is. So as we said, pulsars are born in supernova explosions. They can also be born in some other ways, from accretion-induced collapse of a white dwarf. But in terms of supernova explosion, you know that these are very energetic events. There you have the original object, which might be pretty big, big in size, and now you're shrinking it down to very small size, and there is a huge reduction in the radius. Of course, the outer envelope is ejected, and the inner portion implodes, and the released gravitational potential energy is what throws the ejecta out. So let's look at the implications of this size reduction. And this is what was appealed to, and people felt happy about, that they understand why we see high magnetic fields in neutron stars, and also see high rotation speeds. And people invoked initially simple arguments of flux conservation to understand the high strength of magnetic fields, surface magnetic fields. If you begin from, let's say, some modest magnetic field, like field strength of, let's say, 100 Gauss for the original star, and have a 10 to the 5 reduction in radius, you will have 10 orders of magnitude advantage and amplification for the surface field. Similar argument was used for high rotation speeds, invoking ballerina effect, where conservation of angular momentum would lead to fast spin. It turned out that once people looked at it carefully, they realized that the pre-collapse cores may not have such high enough spin to gain, even after the gain of about 10 to the 10 factor, it may not explain the presently observed spins. And similar thing about magnetic fields. But about the high spins, that was one puzzle to be solved. And there was another puzzle to be solved about this high space motion, or very large space motion. In the sense, these objects move through the space at speeds of hundreds of kilometers per second. And so there was a very nice mechanism that was suggested, and I always make it a point to mention it for its simplicity, which explained in one shot two things. One is the origin of the fast spin, as well as large space motion. And this is tied up with a simple analogy we know of a football, that you kick at the center, the football moves straight along the direction of your kick. But if you kick it off center, you will see it spinning and also moving in the direction of the kick. And so now, by an off center kick, you can produce both fast spin as well as space velocity. How the kick comes about is a matter of detail. People have talked about neutrino emission or asymmetric supernova explosion to have the equivalent recoil as a reaction to imparted to this compact object, which is set in motion and also set to spin. But if this were to be true, you must have observed that as the football moves, the spin axis, the axis around which it's spinning, has to be perpendicular to the direction of its motion. Indeed, recent data on young pulsars supports this expectation, and of course there are other details that are yet unknown in terms of duration of the cake, the all the other complications of and how do we know that this is the spin axis? Why not 90 degrees offset from what we see, and so on? That's tied up with the interpretation of polarization, which we'll come to very soon. But as these objects move at fast speed through the medium, where the speeds of their motion are way above the local ambient, the local sound speed in that medium, and so they will produce a shock, and they do produce what are called bow shocks at the in front of them, and these are seen in even other wavelengths as beautiful nebulae that basically show the wake that is produced by this motion. They might appear like different shapes. In this particular case, it's guitar nebula, and this is tied up with this particular pulsar, which is moving at 1,000 kilometers per second. Okay, coming back to pulsars themselves and their emission, we call them lighthouses because they indeed are like lighthouses, and this basic picture of lighthouse like emission mode in terms of that the light is rotating, the light source is rotating, and when it flashes past us, we see a pulse of light every rotation. This was suggested pretty soon after the discovery of pulsars by Tommy Gold and Franco Pacini, but one still did not know what the real mechanism of this radio radiation is. And that became clear through this famous observation of the Vela pulsar and its creative interpretation by Radhakrishnan and Cook in 1969. What they saw was, when they zoomed onto the pulse, they, as shown in the on the right side of the slide, they saw this pulse profile, which is how the intensity changed during that small interval, which repeated every after interval of the rotation period. But within that, they saw, let me try to get my cursor. Okay, they saw the plane of oscillation of the electric field of the electromagnetic radiation that they were receiving was rotating systematically in a S-type fashion here, as shown here. And that they interpreted in terms of a cone rotating past us, or relatively speaking, the observer sampling a part of the cone, which is shown at the bottom here, and which has got spokes like on a bicycle wheel. And if you sample this pattern at some distance from the center and look at the orientations of the spokes with respect to some reference, let's say vertical here, you will find a systematic change of this orientation. And so if they interpreted this to be the structure of the magnetic field as would appear to an observer looking down on a dipolar field and the pole associated with it. And so this readily sort of interpreted the radiation as coming from the magnetic poles of the star. And the exact shape of it, as it depends on the distance from the center and also the inclination of this cone with respect to the rotation axis, one could now use this the other way. By studying this pattern, one could infer about how far you are from the center and so on and so forth. So these are routinely used to learn about what is called the viewing geometry. But what was clear is that the magnetic fields are so strong that if emission is occurring due to charged particles moving along the field lines, that any transverse momentum, any departure from the curved field line, which will appear as a component of motion perpendicular to the field line, that momentum will be radiated instantly, and that's the radiation that we'll see. Except that now in the process, the charged particles are constrained to move along the curved field lines like beads on a string. Of course, if they are moving at fast speeds, they will give out radiation in a narrow cone associated with the Lorentz factor that they have. And basically the energies will decide how narrow cone in which they will radiate. But what was clear from the fact that you are looking at radiation from a small object, but you see so much intensity, so much distance away from the object, you can estimate what is the equivalent black body temperature that this object should have to produce the amount of radiation that we see at this frequency, or the frequency of our observation. And it turns out that this is not the physical temperature of any entity, but this is an indicator of what is the brightness equivalent of in terms of. So that's about 10 to the 30 degree Kelvin. You know that there is a limit of 10 to the 12 Kelvin for incoherent radiation. If it increases beyond that, some internal processes, absorption and so on, take over to regulate it to that level. And so it is clear that there must be a coherent process involved in producing this radiation. So it is clear, regardless of whether we understand the details of the radiation mechanism, that we are looking at fast rotating magnetized, highly magnetized neutron stars with a well-defined rotation axis and an arbitrarily inclined magnetic axis, wherein there is a co-rotation is possible up to a certain distance and this is called the light cylinder, where if you go sufficiently far from the axis of rotation, you will find that if it were to rigidly rotate or co-rotate with the central star, you would need higher and higher tangential speeds, and at some distance you will reach the tangential speed equal to speed of light, beyond which the co-rotation is not possible. Even before that, it begins to break down and creates distortions. But that apart, if the field lines manage to close within that, they remain closed. The ones that do not manage to close within that distance remain open. Of course, they don't have monopoles here. The lines will eventually close through the circuitous path through the medium around it, and so on and so forth. But now it allows you a path for things to flow out, and this is what actually happens in the case of radio pulsars, and we'll see how that relates to the radiation that we see. Okay, but before we go further, let me make it a point which is not generally appreciated, is pulsars are one of the lowest frequency emitters of electromagnetic radiation. How low the frequency is? It is the spin frequency of the pulsar. Now, what is it radiating? It's radiating electromagnetic dipole radiation at that frequency. And that is one of the key mechanisms or main mechanisms through which it's losing energy. So if you take a magnet and rotate it, it will radiate this electromagnetic dipole radiation. Now this radiation at such a low frequency cannot get very far because the surrounding medium does not allow propagation of such low frequency radiation, because it's filled with material, particularly free electrons, which have a cutoff frequency for propagation of waves below a certain uh, frequency, and that happens to be a few kilohertz. Whereas most of the pulsar spin periods suggest that we have this radiation at much smaller frequency than a few kilohertz. So what will it do? This radiation pushes against the medium, which is trying to stop it, call it radiation pressure, and then there's resistance from the medium itself, not getting pushed further, and so some equilibrium size is attained, and you land up with a nicely formed cavity around pulsars. This were discussed by Rees and Gunn early on, and we will see an example of that in the further talk. But what reaches us is not this low frequency radiation through which it's losing most of its energy. What reaches us is this radio radiation, which is in megahertz and gigahertz, and which increases as we go to lower frequencies. It has a non-thermal spectrum. Okay. So let's ask how an isolated pulsar evolves once it's born. You have this magnetic dipole radiation that we just talked about that will cause loss of energy, and the energy comes from the stored rotational energy, and so it will amount to slowing down the rotation. In addition to this radiation that a rotating magnet gives, you also will know, as you use, many of you might be using such a device on your bicycles to light a bulb when you travel in dark. You use a small dynamo based light, and so what is there? You have a rotating magnet which produces some potential difference, which you connect to a small bulb. And so this dynamo that is operative even in the case of pulsar would weaken if you pedal slowly, for example, as you do on a bicycle. So I will not go through these equations, but to tell you that this understanding that the magnetic dipole radiation is the loss mechanism for the pulsar to lose its rotational energy, and then we can measure how the rotation is evolving. We can measure its period today and how the period is changing, or the spin rate is changing. And if we equate that to the typical dipole radiation that entirely accounting for it, then you can get an estimate of the magnetic field. You can also get an idea about how it has slowed down over time by appropriately accounting for changing rate of slowing down. Okay, but as it gradually shows a secular lengthening of the period or slowing down of the rotation, you will once in a while find tiny discontinuities in its rotation history, and those are called glitches. People liken that to star quakes, and you have change of something which amounts to change of the period by a tiny amount here, 1 part in a million or 10 parts in a billion, in that general range. But that change remains. Only part of it could be recovered. For example, if the period was lengthening gradually, you will suddenly find that the period shortened by a tiny amount, and then again it continued that overall trend. But what this does, the reason for mentioning this is that this is our way of learning about the details of this glitch, as well as the way things recover, or the amount by which they recover, and the time scale over which they recover after this discontinuity, tells us a lot about the interiors of neutron stars, which are otherwise difficult to probe. But in terms of general life, that is objects will follow. You will find that they are born with some initial magnetic field. This is a diagram famously known as BP diagram. B for magnetic field, here P for the period, and pulsar population can be shown here. It's basically appears as a big island here, a cluster of objects in this overall region. So typically they're born in this window of magnetic fields and short periods, moving spinning very fast initially, and as they lose energy, they slow down. So, and in that time frame, the magnetic field doesn't change very much. So they practically move horizontally in this diagram. But when they move this way, you will find that their dynamo is becoming weaker and weaker. And when the dynamo reaches a threshold strength or weakness, the dynamo action is no longer effective for something else which is responsible or which is at the heart of the radiation it produces. So you'll find that it lived as a radio pulsar up to this point, and then the dynamo became very weak, and then you will see that it's no longer seen as a radio pulsar. It's still there, very much there, and has the similar magnetic field and so on. It can be saved and brought back to life if it gets some help, if it finds a companion who can help it. And the spin up through help that can come from basically patting it, giving it angular momentum, and which can be done through accretion of matter, where the orbital angular momentum can be deposited onto this compact star. It can be done only if you have a companion to help. So in binary systems, if this compact star has a companion, which if it happened to be a massive star, which will be ready to help rather quickly, and before anything happens to the magnetic field, the star can be brought back to life. This line here shows the maximum rate at which it can help. That means the maximum accretion rate. And so it can be spun up only up to this period. And that depends on the magnetic field. So you will find that a massive star which evolves rather quickly will be willing to help more readily and more quickly before the star has lost its or reduced its magnetic field. An intermediate star, mass star, might take a little longer. By then, the neutron star would have lost or reduced its magnetic field, and then it can be, when it's brought back in this region. If it's a very low mass companion, it takes a very long time to evolve, and ready by the time it's ready to help in terms of accretion, the magnetic field is reduced by orders of magnitude, 3 to 4 orders of magnitude. And then when it's brought back, it will be in this region, but now you can see that it can be spun up to very short periods. This is where low mass X-ray binaries are sort of the path to creating what are called millisecond pulsars. But what is remarkable is that most pulsars are born in binaries, and depending on their companion and whether the companion survives the first explosion, they will be there to help them in the later life when they lose their dynamo action or weaken their dynamo action to bring them back to life. So their life histories differ based on what kind of companion you have. But what is remarkable is that when the first millisecond pulsar was discovered, it was discovered as an isolated pulsar. It had no, apparent binary connection. But Radhakrishnan and Srinivasan, in their very insightful paper pointed out that this pulsar, even if it appears as an isolated pulsar, has an untold story of its history in a binary system. Now, it must have gotten rid of its companion eventually, but it must have been held by the companion in the manner that we just described. And indeed, so you have seen now many examples, even in action, where the low mass X-ray binaries are caught in the accretion phase and are spinning up the compact object in the manner that we described. Of course, the most celebrated binary pulsar is the one discovered by Taylor and Hulse in 1974 from Arecibo telescope, which was a relativistic binary in the sense both of them neutron stars moving in a very short duration orbit and very tight orbit, and they this provided when they did careful timing observations of this pulsar, which was already the promise of that was discussed early enough. They could see the small change in the periastron passage changing with time, and which is what would be expected based on prediction of relativity, where uh, the energy loss from the system through gravitational radiation would also affect the orbit characteristics of this binary, and that was detected and compared with the prediction of the GR, and you can see the match was more than perfect. And so this was an indirect evidence for gravitational radiation, a system of compact stars going around. And of course, they will eventually spiral in and give rise to the big event that similar to what LIGO has detected. Now, while many of these predictions of more detailed predictions have been checked with this binary pulsar Hulse and Taylor system, now there is a new lab gifted to pulsar astronomers, which has it's a double pulsar system where both of them are radio pulsars. This allows you to resolve certain ambiguities about the inclination of the orbit and so on, which otherwise stop you from probing things further because you need to assume those values in the absence of direct evidence. So many more GR tests are possible, and people should stay tuned if they're interested in. How much time do I have?
Yeah, it's okay. You could continue for another 15 minutes. 10-15 minutes is fine.
Okay. All right. All right. Okay. So one of the special things about millisecond pulsars is that they are ultra-stable clocks. As we said, normal pulsars in their normal life, when they're born with high magnetic field, they slow down and they are losing energy reasonably fast. And then they lose, it's like spending a lot of money quickly and becoming bankrupt. And then finally getting back to life and getting some resource. Next time around, having learned the lessons from the previous life, people can see that uh, they could become misers. Millisecond pulsars are exactly that. They spend energy at such a slow rate that they can live for much, much longer time than they lived in their first life. How long? They can be there for, even 10 giga years of that order. So they, as some people say, milliseconds pulsars live forever. So because they're spending less and slowly, they also slow down very slowly. to the extent of 3 orders of magnitude slower than the normal pulsars. So 1 part in 10 to the 18 seconds per second. So that's how they offer themselves to be one of the competitive clocks. Timekeepers, they compare well, or sometimes they're better than the terrestrial astronomical clocks. And people have been hoping that an array of pulsars, collection of such pulsars over a volume of space, monitored for their locations and arrival time of pulses from them, properly interpreted, could provide a system to detect gravitational wave background or gravitational waves from whatever epoch of interest, including the discrete events. So people have been looking at this possibility, and there are efforts by a large number of groups across the world to do this. These will be probing gravitational waves in the nanohertz range. And it's simply the inverse of the kind of timescales over which this monitoring is typically done. So that's how it's sensitive to those frequencies. Okay, let me run through quickly about radio pulsars. How many are they? We now know, this is an old slide, particularly for the number that I mentioned. There are more than 3,000 pulsars now. And we know that there are about 1 lakh pulsars in our galaxy, of which only about 20,000 might be pointing towards us. As you know, unless you are in the sweep of the cone of radiation, you will not see pulsar radiation. So you miss out on almost 80% of them. Of the 20% that you will see, which is about 20,000, we already have about 1/6 of them already discovered. So you will have large number of pulsars yet to be discovered, and I'm sure many of the youngsters in the audience would be doing that eventually. So what we see pulsars as, in terms of their actual signal, is as a characteristic signature of them is through their average behavior. And so you use thousands of such pulses, available over, let's say, an hour or so, and put them together to build up what is called an average profile, where you will see each pulsar has a signature. Each pulsar has a detail which is different from other. There will be some broad commonality between them, but in terms of the signatures, many people actually, just by looking at the profile, remember the name of the pulsar. So they're so distinct. Of course, don't worry about these other curves here. Some of them are the polarization position angle curves, like the S-shaped curves that we saw. Okay, but when you look at them on a pulse by pulse basis, they're very erratic. They have a very stable average profile. If you observe it today, that average profile will be similar to what you observe 10 years later, and so on and so forth. But in terms of their one pulse to the next pulse, almost look like nothing is similar to each other when you look at them. And if you stack them like this is one such picture, you will find that there is a lot of random variation of their intensity and location. Of course, although it's confined to the window. So when you average these together, that the envelope of all this, average of all this, is a stable profile. Now, while they radiate in radio, do they radiate only in radio? No, some of the pulsars are seen to be bright radiators even at other energies, optical
They,
wavelengths. Yes.
if I could just, there was a question which I thought maybe clarification here may be useful. Is that
Okay.
okay? I'll
Yes.
Pritpal is asking that about the binary pulsar,
Hmm.
and that the rate of pulsation is periodic and therefore it could be used. And I think when you mentioned about the variability of single pulses, is where she's asking whether how can we get if there is variation in single pulses, how. I think that is what
Yeah.
that is.
Okay. So if I understand the question right, the
Shall I
question
read
is
out
about.
exactly the wordings she has? There was a discovery of a binary pulsar in 1974. The rate of pulsation varies periodically. Now, if this pulsar varies non-periodically, how can we get light curve of this pulsar? I, I,
Yeah.
I
So I
thought it
think
was.
yes. So from pulse to pulse, there is large amount of variation. Okay, but still confined to a window which is called the pulse window, and this is still a small fraction of the period. Okay. Now, while the exact pulse shape, as in the previous slide, okay, even if this individual pulse shape differs from each other from pulse to pulse in a wild manner, when you average them together, thousands of them, it attains a stable shape, and that is not changing from 1 hour to the next hour, and so on and so forth. Okay, and so the timing, arrival time of or associated with the some fiducial point of this, okay, or this profile as a whole, is what helps you in timing the pulsars. For pulsar timing, you almost never used single pulses to time. Okay, you might use them to time something else that is happening, which is leading to this erratic pattern or seemingly systematic pattern in some cases, which one of the examples we will see. But the envelope, the average of thousands of pulses, although each one of them might appear erratic, but still within the window. Okay, so its arrival time or its location of bright intensity does not go beyond this window. So at the most, you will have an error of this size. But even to do more accurate timing, you can use the average pulse, and that's the routine way of doing the timing. You never use individual pulses unless they are very stable. Okay. Does that hopefully answer the question? And this is how one can detect changes in the arrival times and Doppler shifts and the possibility of pulsar being in a binary and so on and so forth. And also use them as an array of pulsars uh, to detect gravitational waves and so on.
Yeah, in this
Okay.
connection, there was another question. If it is okay to,
Yes.
uh,
Go
so
ahead.
yeah, actually, Mevan Lingdo has been asking for a little more clarification on how they are used for detection of gravitational waves.
Yeah. So if the gravitational wave passes the volume, the regions where the pulsars are located, uh, you will find that whichever way you want to understand it, space-time curvature or any other way, you will find the arrival time of the pulses from the pulsar, uh, because it involves the travel through this modified space-time, will differ when that curvature exists, and it propagates. You will see changes, and you might see changes in a coordinated way depending on you know various points in space, how signals from them show any deviation from the expected time of arrival, and it is interpreting those in a coordinated way that you might infer about certain distortion of the space-time in that region and its evolution or propagation through that volume of space. Does it
Thanks.
answer the question?
Yeah, yeah, thanks.
Okay. So this is a very challenging task. I hope people will succeed one day. It's not easy, and particularly not easy in because as you know, pulsars themselves are, they're okay to a certain extent, but they're not uh, uh, very, very well behaved. Okay, they're not ideal in any form. So one always chooses the ones which are better behaved and uses them in this array. Okay, so let me proceed. I was just saying that it's not in radio alone that pulsars radiate. They also radiate in other wavebands of the electromagnetic spectrum. And sometimes you will find, as in the case of Vela pulsar, for example, there is a beautiful interpulse at gamma rays, which is there absolutely no trace of interpulse. And the interpulses come from radiation from the other pole in this dipolar geometry. And that requires a very special orientation of the magnetic axis with respect to the rotation axis. Anyway, let me skip over this and just say that the radiation comes from this cone of open field lines, which is aligned with the magnetic axis. And you see radiation coming from low frequencies from outer regions and high frequency from lower regions. And the evolution of what is called the hollow cone of radiation and its width with frequency actually matches reasonably well with the dipole geometry. But coming back to this main point that you have extremely high brightness as as an equivalent black body temperature, suggesting highly coherent radiation, like in masers or lasers, where a large number of charges are radiating together in phase, where the radiation fields add rather than the intensities. And so you will have n square gain if another number of particles radiating together. So without this coherence, you can actually do the sums. None of these radio pulsars would be visible with the kind of sensitivities we have, given that the signals travel and come to us from such large distance. So to produce this large degree of coherence, you require members to be coherent. So the large N is required. You need large charge densities and current densities and how to generate these. And that is done by this dynamo action, which produces large electric fields and large potential difference across a not very long length scale, about 50 meters or something. You have 10 to the 12 volts of potential difference over 50 meters or so. And this acts as an accelerator. Throw in any charged particle there, you will find that the electric field will accelerate it to what kind of energies? TeV energies, tera electron volt energies, right? So you will find that such highly accelerated particles become the seed for further action that we're going to see. So it was shown by Goldreich and Julian that the magnetosphere is not a vacuum. Okay, the region of this cone about the magnetic axis is filled with charges, and so in their charge-filled magnetospheric model, they had all the details, which I'm not going to go through, except to say that there is this accelerator in only certain regions. Elsewhere, the charges rearrange themselves to cancel the electric field, and so where it cannot be cancelled, you have this large electric field, and this electric field in that small region above the what is called the polar cap on the surface about the magnetic axis is a small region. There are also similar regions believed all the way on the boundary of the open field lines, and so on and so forth. So except there, everything is has electric field 0 nominally. Details show that it's not exactly 0 all the way. But okay, so you have this region, the polar cap and central region where the acceleration can take place. And these accelerated charged particles, when interacting with the magnetic field, which is curved, produce electron-positron pairs. And if they are produced within this height where the electric field is non-zero, you will find one sign of charges will move one way, the other sign of charges will move the other way. But outside this, if the charge, if so, they will as the charges move along the curved field line, they will radiate energy in form of gamma rays. The gamma rays interacting with the magnetic field will produce electron-positron pairs, and this process will continue to almost creating an avalanche of pair production, where you have a large number of electron-positrons produced through this cascade, except now that both of them are moving in the same direction because there's no electric field to separate them, treat them differently. So initial momenta will continue to show up, and because the electric field outside this region is largely zero. So what we have is electron-positron plasma moving along the curved field lines and radiating to produce the radio radiation that we see. Of course, the key details of this mechanism, how the coherent amplification is really attained, is not very clear. So the overall picture we have seen, we have a powerful dynamo with large potential difference across a small gap, and this produces acceleration of charged particles which radiate gamma rays or high energy radiation, which interacts with the magnetic field and produces electron-positron pairs. And this is an example of radiation or energy turned into matter. Okay, the pair production is a beautiful example of that. So you have a relativistic particle flow along this field lines, and because the field lines are curved, the charged particles experience acceleration, and accelerated charges radiate, and that's the tiny radiation that we see. It's a tiny fraction of the rotational energy loss rate. Okay, I'm going to skip over this and just show one final thing which is tied up with this large flow of charged particles along this cone, the radiation cone. We never knew how much of energy is taken away by the flow of charged particles. Remember, to produce the coherent radiation, we require large number of particles, and they're moving relativistically, right? So there's large current density, and so we know that so much of energy is carried away by this flow, but we never knew how much exactly that is, because the radiation that we see in radio is a tiny fraction of this, could be tiny fraction of this total energy it takes. But this was clarified for the first time by a very beautiful observation of what is called, what I call a part-time pulsar. It's an intermittent pulsar. It works like me, works for a few days and doesn't work for weeks. And you will find that this is how it was observed. It was active and producing radio radiation over the days where you see these measurements. And then there was a long gap, nothing was happening because you couldn't see the pulsar, no radiation from it. It was nulling. It was going into a quiet state, and then it was becoming active again. Now we know that this is how we normally look at how over a long time scale the pulsar is slowing down. So this is the change of frequency of its rotation, which was seen to change in the expected fashion. But when it was active, it was slowing down a little faster. And this provided for the first time an indication of how much energy loss, extra energy loss must be occurring on top of the dipole radiation, which it's always doing, whether it has this large number of particle production and flow of charged particles taking the energy away or not. So there is a steady energy loss, and then there is energy loss which is subject to the pulsar being active, its machinery to produce this large number of charged particles and flow is active or not. So you will find that this provided the first ever indication of what that energetics associated with the charge flow is. And it turns out, after doing all the sums, that it is found to be consistent with what Goldreich and Julian had predicted as the charge and current density for given the pulsar parameters that you have. So this is a real triumph of the theoretical correctness and the prediction. Okay, I'm not going to go through this. I will just say that now there are techniques to map the regions which you don't normally see. What you see generally is a small cord-like cut. But if the system is doing some systematic rotation, then you can imagine that even if I sit here and do the measurements, I will see different parts of it coming into my view, and I can put them back to create this picture which has been produced. This was a picture where you see the hollow inside because you were cutting the cone at some distance from the center. But if you were to cut it close to the center, you can construct a picture of the cone and its emission pattern even more completely. You can observe different frequencies, and you can combine this measurements and see how similar those are. After all, charged particles are moving along the field lines from down to outward, and actions that are happening of particularly spotty emission that will be along a column of charged particles. And so you can actually relate what is happening here to what is happening there at later time, and so on and so forth. To be able to do this kind of studies, you require simultaneous multi-frequency probe, and you can build appropriate equipment and produce such tomographs of the pulsar emission cone. So I will stop here and leave you with this beautiful picture which shows the cavity that I talked about initially, that the pulsar produces about it. When this flow that we just invoked of charged particles, relativistic charged particles, goes and hits the wall of this cavity, the particles will lose energy because you're hitting against a wall, hard wall, and you will produce some sound, some action will be there. And it's in terms of the shock that it produces and a brightening where it loses energy, and it's produced in X-rays and beautiful X-ray nebulosity, tracing the flow of the charged particles along the cone into rings is seen, and the rings are brighter towards you. And so you will see that you can understand this as basically two-ended hose of charged particles with a paint sort of thrown in on the wall of the cavity, and it will paint two circles. The circles will be seen as ellipses if you're looking at it at an angle. And if the stuff coming towards you is going to be brighter because of certain boosting, you will find that you will see traces along of these two cones or the two ends of the hose, like you see the red curves. They match very perfectly with what would be expected from the geometry of this pulsar. And you can put in the hazy pattern where the energy is also spread across in latitude, and have a, just from the geometry alone, you can produce a picture that you would expect to see of this nebula around the pulsar. This is an X-ray nebula. What is remarkable is, remember that I mentioned that you do not see at radio the second pole, radiation from the second pole of the Vela pulsar. which was visible in X-rays. But now, regardless of whether this is X-ray picture or the radio picture, you see trace of the second pole. The unseen pole is visible. Okay, so you see traces on the wall of the sky. Okay, produced by the radiation, which is result of particle flow, relativistic particle flow from this. So excitement continued, and one has also detected precision in this case of this pulsar, which I will not go through unless there are any questions. So, I mean, similar geometrical picture can be produced even for the Crab Nebula, Pulsar Wind Nebula, and you can see that just geometry alone and the two-ended hose of charged particles will produce these kind of pictures on the plane of the sky, which you can study. So I will stop here and leave you with this two potential holy grails to be discovered. Sub-millisecond pulsars and black hole pulsar binary are yet to be detected, and of course possibly detect gravitational waves. I'm sure many of you will be part of this future excitement. Thank you.
Thank you for taking the viewers through the many detective stories related to radio pulsars, theoretical modelings, and observations. Actually, I think I'll ask you to take up Jyotishmita Bora's question. She asked right in the beginning, as you were talking about some of the inferences about what theoretically pulsars could be. So she was wondering, are these calculations 100% true? Since these objects are much far away from our solar system, and you already, I mean, highlighted two of the matches which make us believe in all of these, the cavity being visualized through observations and the Goldridge Julian density match, etc. But maybe some other uh, reassurances to Jyotishmita that we are having verifications of these modelings.
Uh, are you referring to particularly the cavity and so on?
No, actually, Jyotishmita asked this question right in the beginning when you were
Yes.
giving the theoretical, arrival at what could be radio pulsars. She was
Okay.
wondering about, her question was that
Well, them
are all of these
about them
inferences
being neutron
100%
stars.
true?
About
Yeah,
them
yeah.
being
So,
neutron stars.
yeah, I think around that time she had asked, and so I did mention to her in chat that many of the no, I think she was talking when you were talking about the rotating vector model and so on, inferences from that.
Okay.
So
Oh, about
basically she,
polarization and so on.
so probably, given the rich kind of observations and so on, so she's
Right.
asking the match between theory and observations.
Yeah.
How
So
is
the
it
match between
100% true?
theory, yeah, match between theory and observation is remarkably high, except pulsars, as they do deviate from the general rule quite often. There are cases where the polarization position angle switches suddenly to another value which is exactly 90 degrees away. There are situations where the beautiful S curve is not seen. There are deviations from it, systematic and random. Uh, and some of those are being understood as due to deviations from the dipole geometry, which are to be expected when you go very close to the surface of the star. They would be higher order in magnetic field, not just dipolar. And the structure of the magnetic field may not be as nicely described as we have been describing as a dipole structure, which is certainly true when we go far enough, but where the other higher order contribution falls rapidly at large distances is reasonably well described as a dipole magnetic field. Whereas close to the surface, higher order field, higher order poles would contributing significantly, and their effect would be seen. Not only the effect is seen, they are required to be there, because many of these initial actions relating to radiation, because remember, the fields are not highly curved when they start off for the dipole geometry, very close to the surface. So there has to be enough curvature for producing radiation of gamma rays and so on through these charged particles that are moving, are initially accelerated. So yes, there is a lot of stories that are not told in uh, broad brush descriptions that we generally give without going to details. But many of these key features are held on the average to be true, and there is enough evidence and correspondence with the theory.
Yes.
Now, one classic example of how things might still be unclear, and as we go along, we might get better feel for it and begin to estimate. Originally, people used to take the slowdown of pulsars and their period and combine these measurements and equate the energy loss to what is radiated away as a magnetic dipole radiation, and use that equality to estimate the magnetic field strength. Now you have seen that we have shown that the slowdown is not occurring only due to the magnetic dipole radiation. It is also comparable amount of energy is being lost in the particle flow. Now, if one were to really do things correctly, one should go back. If one knew these proportions from observations of the kind that one managed to do on this very peculiar pulsar, part-time pulsar, you will find that now you can estimate how much, what fraction of it is really going into magnetic dipole radiation, and then redo the calculation, and you will find typically the magnetic fields will be root 2 times smaller than inferred earlier. It won't be, of course, an order of magnitude smaller than inferred earlier, but there will be always things like this which need to be growingly accounted for, and more and more correct estimations will become possible.
Uh, I think also when she was asking the question, she was even about the broad picture itself, and so perhaps
Yes.
pulsars are one group of objects where we have very strong evidence for the broad picture to be right in
Yeah.
terms of the geometries and so on, but there is a rich variation over and above that. Would that be fair?
Yeah. Yeah. There are lots of subtle details. We still do not know how they really do the amplification. Okay, people invoke a variety of ways of understanding how this. They involve even laser action and negative optical depths and some plasma process where uh, lots of details which are thrown under the rug presently. But when you face them, and when you look at even the behavioral aspect of pulsars, why does it suddenly switch off? We have
Hmm.
not understood that really well, as much
Hmm.
as we have not understood how they amplify these things,
Huh.
how they produce
In
the
these
coherent code.
in these kind of special features like the nulling you are referring to, or maybe even giant pulses, etc., are there now
Yes,
enough number of objects in these that statistical
yes,
kind of
people
studies have
have done a
given
lot of
us
statistical things. Yeah,
better understanding?
yeah, it has not led to better understanding, but there is at least a basis for asking some of the questions and trying to answer them using the statistics that might be available. Earlier, even that was not available. So now, at least, there is enough statistics available to follow through an interesting question or thought.
Sanket Bangar had asked, and he said later he's clarified because he asked before you actually touched upon it about the interaction of the atmosphere. of the neutron star with strong magnetic fields. But you did discussed it, and later on he says he's cleared. Sanket, if you
Okay.
have any other question on it, you could. Also, anyone, if you have further questions, you could type before we close the breakfast. If you broadcast, I'm sorry for my audio typo. And I'll call in Jayant. Jayant Ganguly from Calicut Planetarium, and they are planning to take over the organizing of the Astro Adda from the next session onwards, right? So, Jayant, I'm just checking whether there are any other questions before calling you in for one question. If I could just the thing is that as far as the emission itself is concerned, it seems like there are so many of the theories, and all of them have some issue or other. But when we see certain peculiarities of features like changes in the emission patterns mode, could it be that maybe more than one of these mechanisms is working, and under different circumstances maybe one works and the other works? The changes that we see, pulse to
Yeah,
pulse
for
or otherwise.
example, I think, for example, there is this pulsar for which I showed the ring bangle structure, right? With this hotspots. That changes its emission mode. It doesn't, although I said it has the fixed signature, it is like somebody having two signatures, one being used for official purposes and one for personal purposes.
Hmm.
So it switches between the two uh, without any warning. And people like Dipanjan Mitra and co-workers have tried to look for corresponding changes in the X-ray emission, and they have found a very explicit correspondence, which is
Hmm. Hmm.
remarkable.
Uh,
Prikpal has put a question again. Prikpal, this was taken up at the time of the discussion, wherein it was mentioned that individual variations are not what are being used when one was doing timing. Some kind of average and then average segments is what is giving that. If we understood the question right, Prikpal, when you had asked it at the time, it was taken up that it would not be the individual variations, pulse by pulse variations, but good number of pulses averaged together. Then you get the
Yeah, so
steady.
if it's,
I hope.
it will be periodic. The pulses arrive periodically, and it changes in the period are understandable either in form of some Doppler shift, binary motion related or otherwise, or any propagation effects that one can account for. And then having corrected for these, things really fall on the top of each other. And if they don't, you will end up refining the parameters associated with what you assumed as the
Huh,
rotation period
huh,
and so on. This is the game of pulsar timing is that initially you may not know what the period is.
hmm,
Even if the pulsar pulses were to behave well, okay, and not vary from one another, even to begin with, you may not know the precise period, because of which you might assume certain period and then they will not line up. And then you use that information that they are not lining up itself to refine the period and refine their rotational history. And the idea is to see deviations from that best modeled trend. Okay? And that's
yes.
the one that gives you extra information on top of that.
I have one question.
Yes.
You spoke about this part-time pulsars, no, which Kramer has put in 2000. So,
Yes,
what is
yes.
the mechanism actually? Why actually we don't get in certain
Yeah.
after a certain period, no, we don't observe anything, and then again, what
Yes.
exactly happened physically there?
Yeah,
Can
so
you?
the one
I
can imagine
believe.
by the way the pulsars, we talked about pulsar death, and we said very loosely speaking, and in fact it's strictly followed. If you really follow the dynamo action and see uh, the the potential difference that is required to accelerate charges to energies that they can produce enough pairs, right? That's the whole idea. Unless you produce enough pairs, you don't have enough to radiate together coherently. So that entire action is tied up with the very basic condition of having enough potential difference produced through the dynamo action. If, for example, somebody does, it's like the electricity failure because somebody shorted, produces a short circuit. right? Everybody loses the, the supply, right? So here it might happen that either the potential difference does not build up to a high enough level to start the engine of acceleration, pair production, cascade of pair production, and unless that is done, you don't have enough charged particles to radiate coherently to produce the kind of radiation intensities we see. So everything can appear to have been switched off if we just drop the potential difference. And this is what happens when pulsars die. Actually, the dynamo becomes weak, and that's why they can no longer produce the radio radiation, because it's tied up with producing coherent radiation. Coherence requires large number of particles. Large number of particles require production of initial acceleration to TeV energies. Okay, and if that is not possible, you do not have the rest of the action ending up in radio radiation. So during the phases of nulling, somehow the potential difference has not built up adequately, as much as it does not during the times when the permanent failure occurs, when we say pulsar died.
It's an evaluation phase of the. It's a part of
Yes,
the.
we earlier thought that older pulsars go through this nulling phase more often, okay, or long stretches of nulling. That's not really borne out by the observations. Pulsars, earlier it was a very simple explanation, and people thought that might be right. And initially there was probably wrong indications that it might be so. But later it has turned out, after the statistics has become better, that nulling is not necessarily restricted to pulsars which are close to dying. They are not sort of having hiccups as they are preparing to die. They sometimes have this well before they're going to reach that deadline.
Okay. So over to you, Jayant. Sir,
Yeah, yeah,
I don't see further viewer questions, so over to you.
yeah,
So vote of thanks.
yeah. I thank Professor Avinash Deshpande for giving a really insightful lecture, and I think all of the participants and all of us have enjoyed the lecture and learned a lot new things about it. Thank you.
Yeah.
Thank
I'm
you.
ending this broadcast. In case anybody has further questions, you could post them on the YouTube video itself. This will be available at the same link now as a recorded session. I'm ending the broadcast. Thank you, everyone.